Hello, everybody. So let's talk about deep learning, CNTK, and F#. Before diving into the topic, I figured I should probably introduce myself. So my name is Mathias Brandewinder. You can find me on Twitter as @Brandewinder. I usually look like this on Twitter, on GitHub, and all these places. And the few things you might want to know about me is, like, first, like from the accent, you might have guessed that I lived in California, which is correct, but that's not where the accent is from. The accent is French. And the other thing you might, which is relevant to the topic today, is that my two main interests technically are functional programming in general and F# in particular. And anything numeric, in particular machine learning, but also forecasting, probability, all that type of stuff. So like F# and CNTK and deep learning are right at the intersection of the things I care about, and this is what we're going to talk about. Why is it that I wanted to talk about this particular topic? I'm going to start with a couple of statements which I think are not particularly controversial. The first statement is deep learning is a very hot topic. Like everywhere you go, people are raving about it, like people getting excited. It's getting all sorts of great results. So I want to do deep learning because it looks like this is awesome. Now, the second non-controversial statement, I think, is that deep learning and .NET is not a hot topic. Like if you look at people talking about deep learning, they will talk about Python, they will talk about all sorts of libraries, but .NET pretty much never shows up. So I mentioned earlier that I'm an F# person or a .NET person, so this is making me sad because like everybody's doing deep learning. I want to do deep learning, but I also want to do .NET because that's the other thing I like to do. So for a long time, I was kind of stuck and thinking like, what do I do? Do I have to jump into Python? I'm stuck. And then it's like maybe 1.5 years ago, Microsoft released a library. So the library is called CNTK and had been used internally for a while. In particular, the thing which was interesting to me is like they released the library with a .NET API. So this was like, aha, fantastic. Finally, I can do deep learning. I can use .NET. I will be happy. So what I want to show is what I have been doing with CNTK, like what you might expect from it, the type of work I've been doing with it, and like how this plays out with F# and why you might care. So the overall plan for the presentation will be in 3 parts. First, I'm going to start with a shallow introduction to deep learning. The reason I think this might be useful is this is a developer conference, so chances are you have at best a shallow understanding of what deep learning is about. So I figured I would try my best to give you a sense for what is deep learning, why it might work, and why people do care about it. Then I'm going to dive into CNTK. And so I'm going to look at first, if you take CNTK, the library, out of the box, like what do you get? How does this look like? And finally, what we're going to see is like, 1, it works. That's nice. 2, it works, but it's painful. That's not nice. So I'm going to show also a couple of things I have been doing with F# so that CNTK is becoming a bit more pleasant to work with. So that's my plan. So let's start with deep learning. What is it? So let's do a bit of a shallow introduction. So I'm going to start in maybe not the most obvious places, but I'm going to go back to a period of time when you played video games, this is the type of thing you saw on screen. Like Donkey Kong, like a whole big historical game. And when you went back in the days when you played games, you saw some things like this, which looked kind of blocky. So these are like 8-bit style games. The reason I wanted to start there was I wanted to consider the following question, is like if you look at the display on the screen, I see something like bonus 7,400. This is represented in like 8-bit style. And the question I want to look at first has nothing to do with machine learning, but the question is, how would I go about building something which represents number in an 8-bit style? So something like this. Every number should be on a grid which is 8 by 8, and roughly the idea is that a pixel can either be a dark or light, and each of them form a shape, which could be a 0, could be a 1, could be a 2, could be a 3, and so on and so forth. So my goal initially will be, can we build something which I press a button and I see a 0, I press a button and I see a 3. If I wanted to do that, what I want, I describe something where I press a button and I see the image. Conceptually, what I think is like when I press a button and I want to see a 1, what I really want is I want the pixels which represent the 1 to light up and the other ones to not light up. So I can think of it maybe in terms of a switch on and off, and when I put it on, I'm going to have a light bulb, which is my pixel, which lights up. So if I wanted to do that, I'm also going to use a small symbol like throughout, I'm going to use an idea which is an activation gate. So whenever I press a button, what I'm going to get is like an electric signal, power comes in. If I have enough power, my gate will give me an output of 1, like yes, this is active, and if not, 0, it's not active. Good. So if I wanted to display a 1, all I would need to do is the following. I would maybe have a button here, on and off. If I put it on, I get power in, comes in the gate, and now is like I would have like 8 by 8 is 64 bulbs on a grid. And I would just, all I would need to do would be to take a couple of cables and plug in like all the pixels which should be active to the gate here. So here I represented like 3 pixels. This one is never going to be on and a 1, so I don't care. This one I would connect, and this one I would not connect. If I have something like this, what will happen is like if I press the button, I will see a 1. If I depress the button, the 1 disappears. So this is a valid system to represent a 1, a 2, a 0. Now, this works, but like it has a couple of drawbacks. Like one of the drawbacks is like if I want to rewire my system and represent a 2, a 6, I will have to unwire everything, rewire everything. This is kind of complicated. So instead of doing that, I'm going to use something like a volume button, which goes from 0 to 10. And what it does is like whenever power comes in, if the volume is at 0, nothing comes through. If it's at 100%, everything comes through. So that's what I'm going to use. And what this gives me now is a system which looks a bit different. So I still have like 8 by 8 bulbs on my grid here. And if I look at my 3 pixels I want to look at here, what I will do is I will actually plug every single bulb to the input signal. So now instead of like a couple of cables, I have like 64 bulbs, 64 cables. And on each of the cables, I have like a power thing which I can slide up and down. And if I do that, now, if I wanted to represent a 1, instead of unwiring, rewiring the bulbs, all I would have to do is like put the power thing on the right position. Like for this thing, which is supposed to be on, I would turn it all the way in. And so now I would get the same result as before. When I press 1, power comes in. This thing is set to 0, so it will not light up. This thing is set to 100%, so this will light up. And this is a 0, doesn't light up. So I get the same result as before, but I get the same wiring every single time. The only difference is like I have like a power button for every output, and all I need to do is like to set them in the right position. What I built here is something which you could describe as a filter. What I'm saying is like the output I want looks like this. What I build is a filter which is 8 by 8 with which all the controls, and the filter is really saying like filter the input to produce the output. And so the weights currently look exactly like the output I want to produce. And I'm not going to insult your intelligence. You could see how this would be very easy to extend to represent a 1, a 2, a 3, an 8, an emoji. Like you can use that pattern to represent any image you could possibly want. So this is good. Now, is like at that point, you might ask the following question: is like this is all great, like Donkey Kong is a fantastic game, bulbs are great, but what does this have to do with machine learning? And so far, nothing. But like the relationship with machine learning is what we tried to do was to build a program where if I press a button, I see the output. Now the machine learning position is trying to reverse engineer that exact same problem. Instead of pressing the button and seeing a 1, what I want is like if you give me a 1, I want the output of the system to be this button is going to be active. So instead of press 1, see a 1, if I see a 1, I want you to tell me it was a 1. And to do this is like all I need to do is I need to reverse the system I just presented to you. Instead of going from the input is on the left side and goes to the right, now my input is going to be the image here, which is like 8 by 8 pixels, which are like a different strength of the signal. I'm going to push them into cables. Each of them is going to go into one of these control things. And I'm going to group them all together into the gate. If enough of a signal comes here, it's going to tell me this is a 1. Otherwise, if the wiring is done differently, it's going to tell me this is a 2. So that's what we're after. So if you were to do machine learning manually in the system, what you would do is like put the image, plug it in, see what the output is, and then start to tweak the controls to see if the output becomes more close to what you want. And so I would maybe move this one up, down, and see a bit what happens. And after a while, I would probably end up with something along these lines. I would end up with like weights. This pixel is not useful in recognizing a 1 because like that's like I don't see it on when it's a 1, so the weight would be 0 or the control would be 0. When this pixel is on, this is probably a 1, so I would have a high weight. When this is on, this will give me some power, which goes here, increases the power, and will activate the 1. This will be a 0, and so on and so forth. So by tweaking the weights, I should be able to create a system which is going to behave the following way. Give me an image of a 1. The output will be, yes, it's a 1. And that might sound like simplistic, but this is essentially what every single machine learning library does. The way you would train such a system is that you would take images where you know the correct answer. You would take an image maybe of a 1. You would pass it to your system. You would compute the output, and then you would look at what it tells you for a 1. And then you would try to tweak the weights so that the answer on a 1 goes up, and the answer on 2, 3, 4, all the incorrect answers go down. And then I would take another image. Maybe I will take a 6, I will pass it through the system, and I will observe the output. And I will again tweak the weights, see which, and I try to adjust the weights so that I get an answer which is closer to what I want. And I would do it over and over and over again. So I would not do it by hand. I would do it by using techniques like backwards propagation. That's the math thing, but essentially it will just change the weights over and over and over again until the system will actually do the following. If you give me an image of a 1, I will tell you it's a 1, 3, it's a 3, and so on and so forth. So let's think for a minute about, so we're trying to train weights. Let's think about for a minute on how should the weights look like if the system behaved properly. So my goal here is going to be take an image and tell me if it's a 1 or a 2. So I have an image, I don't know what it is. I'm going to build like 2 filters, one for the 1, one for the 2, so that if I give you a 1, I want the answer to be 1, and if I give you a 2, I want this one to activate the 2 here. So I would expect, in general, the filter to look more or less the same shape as the shape I'm trying to recognize. But if you look at here is the filter I would actually expect. So what you might notice here is that I have like most of the weights are at 0, like they're white, like these do not really matter. I have some of them which are in black and some of them in red. And so the point which is interesting here is that the red weights are the weights which I would expect to be high, and the black ones are weights which I would actually not expect to be high. Why is that? The reason that is the case is because what my filter should do is that it should activate when it sees an input which is useful to recognize a 1 from a 2. If I see that this pixel is active only in the case of a 1, it's not really active when I have a 2. So I would expect this to be informative to tell me this is a 1. On the other hand, if I look at this pixel in the middle here, that pixel is going to be active if the image is a 1, but it's also going to be active if the image is a 2. So if all I saw was this pixel, is like I could not tell you if it's a 1 or a 2. It's not useful information. So what I displayed in red is really like what the filter should look more or less along these lines. It would highlight all the pieces of information which are specific to a 1 and not a 2. So this is why I have like these pieces here and not the black pixels activated. Now, if I follow on this idea, you might make another comment. Like suppose I take my images, I train my system, and maybe I could end up with a system which is actually much easier, which is using much less weights. In the end, if I wanted to recognize if an image is a 1 or is a 2, the only thing I need is like 1 pixel. Like if this pixel here is active, I know 100% this is a 1, because that's appearing on a 1, and it's never appearing on a 2. So 1 pixel should be enough to tell me all I need to know about the image. Similarly, like if I took maybe this pixel at the bottom, it appears on a 2, doesn't appear on a 1. So if I knew this pixel was active, that's all I need to know. I know it's a 2, and I should not need anything else. So that would work. There would be one benefit, because now is like I need just 2 inputs instead of 64. Would be faster, would be all these things. The drawback is that my system would be extremely fragile. Because if my input had like any maybe flaky signal, if I got like, if for some reason I did a bad read on the pixel here, the answer would be entirely incorrect. So by relying on just 1 pixel, I would get a system which would be very fragile to noise. Therefore, it's like I would expect something like this, which is using more things, and is like maybe one of them will be flaky, but all of them, it's unlikely that all of them will fail together. And so henceforth, like I would want a good system to learn weights which look like this and not like this. Quick comments. So that might look like simple or primitive. This is the model I showed you actually has a name and a famed history. Like this is what people call a perceptron or logistic regression or a densely connected layer. And this is like the simplest neural network you could build. Like the characteristic of it, it has like only 1 layer. So one way to describe what I showed you is like a neural network which is like a shallow learning. And all you're trying to do when you're trying to build a deep learning model or a neural network is that you are trying to configure the network a certain way, and then pass it to an algorithm which is going to try to find weights which make the thing work and give you the answer you want. Another way to think about it, maybe, is what you're doing when you're doing such a thing is like it's pretty analogous to what you would do if you build hardware. What I'm building here is I'm saying like, hey, you're going to get inputs which are going to have this shape. I want you to use these two filters which have a particular shape, put them together. Then I'm going to give you examples, and I want you, the algorithm, or you, the computer, to figure out how to wire this properly so that you get the correct answer. So in other words, you're building like something like a circuit board, but instead of doing the wiring yourself, you give the components, give examples, and you let the algorithm figure out what the wiring should be to get the proper answer. Now, so I said like what we did so far was shallow learning. How about building something which is a bit more complicated or a bit deeper? So maybe one observation I could make is like if I look at a 2 here, my 2 is like 8 by 8 pixels, but I could really break it into 4 by 4, 4 by 4, 4 by 4, and 4 by 4. That's quite possible, so why would I want to do that? Well, if I did something like this, I could start to build a circuit which looks a bit different. Instead of having only one filter which is going to try to recognize the entire image as at once, what I could do is I could build one filter here which is going to try to recognize what's happening in this corner here, one filter here which is going to recognize this corner, one here for this corner, and one here for this corner. And so if I did this, like instead of one filter, I would have like 4 filters. That filter would look at the image and tell me essentially yes or no, I found this pattern in the corner here. Yes or no, I found this pattern in the corner here, so on and so forth. So I would get like 4 reads on 4 sections. Each of them would give me a 1 or a 0, and then if I had like, in the case of a 2, I would get, yes, I found this, yes, I found this, I found this, I found this. I could plug this again into another activation gate, and that would give me the answer of a 2. If I passed a 1 to this circuit with like 4 circuits, now what this would tell me is like, I didn't find this, I didn't find this, I didn't find this, I didn't find this. I would get 0 and 0 input here, and so this would tell me this is not a 2. Now the thing which is interesting here is I could start to use it also for other shapes, because now you might notice that this shape here belonged to a 2, but was also a shape which was a building block for a 3 or other things. So what I'm doing here is like instead of trying to recognize an entire shape, which is a 3 or 1 or a 7, I'm trying to recognize like simpler shapes, like something which is here is a straight line, here is a curve, all these things. And now what I'm saying when I'm saying like this is how a 2 looks is I'm saying a 2 is really a curve, a curve, a curve on a straight line like this. So I'm, instead of trying to recognize the whole thing, I'm trying to recognize like smaller patterns, and then say when you say this pattern and this pattern and this pattern, this is probably this. And the way this would look at that point is like what you're building is a model which is really stacking up more and more and more sensors. So I would have like a first layer here which is saying like look at patterns which are 4 by 4, and then is like plug them in. So I would recognize one pattern, another pattern, and so on. Tell me yes or no, did you find it? And then you would plug all the outputs of this into another array of sensors, which are going to tell you, did I find this combination of patterns or this combination of patterns? And you could keep going and going and going and recognize like simple patterns into complicated shapes. That's what you do when you do a deep learning model. So the blocks you build, each of them is an array of filters of similar shapes, which do the same thing. And then is like the way you build your models, you're going to say my first layer is going to recognize like small shapes. I want like 16 sensors, and then feed that into a layer with like 8 sensors of size 4, and so on and so forth, up to the answer you want. So in other words, like what you're doing typically when you do a deep learning model is that you build an architecture for how your board should look like, put the sensor where you want, and then pass examples to learn, and hopefully if everything works, you get the correct answer. So recap. When a deep learning model is a model which is composed of layers, each layer is an array of filters or an array of sensors which are going to recognize the specific patterns. And then it's like you will take examples with known answer, you will feed it to the system and let it converge up to the moment the system learns how to produce the correct answer. Now that I hopefully give you a bit of a sense for how a deep learning network looks and what it's supposed to do or why it's supposed to work, let's take a look at CNTK. So if you take CNTK out of the box, first, like, what is CNTK? So CNTK is one of these algorithms, one of these acronyms which Microsoft is like so good at producing. It's just the worst name for a library ever, probably. But CNTK is a shortcut for like Cognitive Toolkit. So not the most fun acronym. It's an open source library. You can find all of it on GitHub. The thing which is particularly interesting about it is that it runs on a CPU, so you can run it on your local machine, it runs on the GPU, and it can even run on distributed GPUs. So this is nice when you want to do like really heavy computation. It's also used internally on a couple of products at Microsoft, which is one of the reasons I cared about the library. Because like things work at small scale, but if the library was good enough for Microsoft to use on Bing, I'm assuming that it's going to be good enough for my tiny data sets home. So like, that was like something which I took as a sign that this would be working. Otherwise, the core of the library is written in C++, and on top of it, you have a bunch of APIs. You have a Python APIs, you have something called BrainScript, which is a language specific to it. You have like a C# or .NET API, a bunch of things. And at a high level, if you've been looking at other libraries in deep learning, like TensorFlow, pretty much everything I'm going to talk to you about CNTK is correct about TensorFlow. Like the ideas are the same, some names are slightly different, but like it should translate pretty easily. So what does CNTK do? If we do deep learning, we need a couple of things. It's like one is like in our problem, we had an image we wanted to predict a number. So it allows you to predict how the input of your model is going to connect to the output. Second is like if you want to train the model and pass it examples, you need to be able to read or acquire data. So it gives you like ways to read inputs into the model. It gives you a collection of algorithms so that you can give it examples and it will tweak the weights or learn the correct weights. And of course, it will also allow to save and open a model, because once you trained it, there's like chances are you want to use it in production. So you can train it and then you can consume it. The core components of the library, you have a couple of things. The first, really the base element is what people in CNTK called an ND shape, or also a tensor. Like this is what you find in TensorFlow as well. You have functions. You have input variables, parameter, and constants. You have trainers. So trainers are like things like how do I want to update my weights? And you have, I'm going to develop a bit on tensor, function, input variable, and constant in a second. And you have like readers, and specifically mini-batch readers. So readers are actually kind of important because when you work on a very large data set, like say terabytes of data, you cannot read everything in memory. So what you will want is that you will want to read a lot of examples to feed your model. If you have terabytes, you cannot simply open a CSV file and do it. So a mini-batch reader is going to be doing something like take the data set and start to read in different places efficiently to pull data to feed into your model. So that's built also in CNTK. So the first word I used was the core element in CNTK is a tensor. And so you might ask, what is a tensor? And it's like, I didn't know initially what a tensor was. And it's like after a while, I realized like a tensor is really a very pretentious way to say I'm working with an array which could have like n dimension. This is all a tensor is. So a tensor or an ND shape is like an array would be a one-dimensional shape. You could have a two-dimensional array or three-dimensional and so on and so forth. This is what a tensor is. The reason tensors are so important in machine learning is a couple of ones. One of them is it's quite convenient because if you can represent everything in the shape of an array, then it's going to be easy to compose models together. You have like one core component and you can compose these things together. The second one is like tensors or arrays work really well with GPUs. And now the third reason is like actually a tensor works to represent pretty much anything you might want, or like with a bit of effort maybe. To illustrate that, so a 2D tensor would be probably what you would use if you worked with a black and white image. Like what this is, it's an image which is going to have pixels by pixels, and so my 2D tensor would be like a 2D array which contains numbers, how dark, how light is the image. If you had an image which was in a color, like red, green, and blue, what you would need then is a 3D tensor. You would have one tensor for the blue layer, one tensor for the green layer, and one 2D array like for the red layer. Put them together, now you have a cube. And if you didn't have an image, but maybe you had a movie, all you need is like another dimension, and you would do a 4D tensor. And so a movie would be a sequence of RGB images, so you'd have the same thing as before, and a fourth axis, which would be time. And I'm sure there are usages for 5D tensors, but I can't think of one, so it's like I will leave it at that. But like you can represent pretty much whatever you want with a tensor. So what we want to represent is a model which takes an input and gives me the output. This is what's called like a function in CNTK. What we're doing is, in our case, if we wanted to recognize an image by using like weights, what we would do is we would take an input variable that would be a 2D tensor, an image which is 8 by 8, black and white. I would have like parameters which are my weights. That's also a 2D tensor, 8 by 8. And my output is going to be a 1D tensor. It's a 0 or a 1, like depending on whether I found like a 1 or a 2. And so the way the function would work is like simply by doing the following operation: take the input you found here in the tensor, multiply by this, weight, plus this times this, plus this times this. So what you're doing is a glorified 2D array multiplication that will give you a number, and then is like depending on the sum it all together and pass it into this gate, which is going to say if the output you got from the function is higher than something, then it's a 1, otherwise it's not a 1. So that's what we're trying to build. I could write this also like in standard like .NET code, like in F#. I would probably write something like this. My model is taking three things actually. The input is going to be my image. That's a 2D array of numbers, like 8 by 8. I'm going to give you also an array of weights, 8 by 8, and also a threshold, which is going to be like when should you activate. And what the function does, or what the model does, is simply take the input, take the weight, multiply together, compute the sum, and if the sum is greater than the threshold, yes or no, it's a 1. So this is what you will get at the end when you have a trained model. This will be correct. The problem is that if I look at it this way, there is one issue, which is like you have one step. If you knew what the weights were, you would be done. The problem is like the reason you need a deep learning library is because you don't know the weights in the first place. What you're trying to do is like use an algorithm to actually find the weights. So to make that work is like I need to distinguish in my function what are actual inputs, like the image is the image is the image, I cannot change it, and what are the weights, and the weights are things the algorithm is allowed to change to make the answer closer to what it wants. So even though all of these are floats or tensors, is like some of them the model can change, some of them the model cannot change. So I need that distinction, which is why in the core elements of CNTK you have a function, and a function is going to compose input variables. So that's a tensor, which are your input. It's going to use also parameters, which is also a tensor, but that's the thing the model is actually allowed to tweak. And a function is going to be an expression which combines these two things together to give you a model. So now I talked a lot, and I didn't show any code. So how about I look at this and we try to actually build from scratch with CNTK something which actually recognizes ones and twos, like the way I described it to you. So what I said before is like I would expect the filters to be learned by the model to look something like this, like red weights for the ones and like the red weights here to recognize the twos. I'm actually going to use a small trick. And if you think about it, if I'm only trying to recognize ones and twos, I could use one filter only and not two. So the way I'm going to do this is like in yellow here, I have the filter for the 1. In blue, I have the filter for the 2. And I'm going to collapse them into a single filter. The trick I'm going to use is the weights which are in yellow are going to be positive numbers, so that when the filter gives me a positive number, I know it's a 1. The weights for the blue weights, which are for the 2, are going to be negative numbers, so that when I'm getting a very negative signal, I know it's a 2. And if it's not a 1 and if it's not a 2, it's going to be at 0 because the model will not know. So I'm just putting everything together, and I'm doing something which is if it's very positive, it's a 1. If it's very negative, it's a 2. And if it's in between, it's like the model is not quite sure. So let's do that. So I'm going to go to Visual Studio Code, and I'm going to show a bit of code. So the first thing I'm going to do is I'm going to load my library here. So I'm going to load CNTK and all these things. Let me also reduce this a bit. And so I'm going to work literally on the data set I described. So I'm going to, what I did is I created a big data set of 64 images. And the 64 images I created were either ones or twos encoded in 8-bit. So what you see in the data set is like I have first a column here which is marked as a label. So this is saying like this image is a 1, this image is a 1, this image is a 1, and so on and so forth. I have 32 examples of ones. And then I have like 32 examples of twos. I was not very smart, so I marked this as a 0. So when you have a 0, it's really a 2. Like in hindsight, this was perhaps not the best encoding, but hindsight is 20/20. And then is like what I have is like for each of these images, I have pixels. So I have 8 pixels, which is the top row, 8 pixels, 8 pixels, and so on and so forth. And to make things a bit more interesting, is like I introduced a bit of noise also in my data set. So you can see, for instance, like this is an image of a 1, and in this one, I have like 1 pixel which is different. So I took like 32 images and just sprinkled a bit of noise to see like if the model was actually somewhat robust. So now what I want is I want to use this to build a machine which is going to tell me when you give me this image, is this a 1, is this a 2? How do I do that? So yeah, that's the inputs I'm using. They look like this. So what I want is I want something which is doing like take the pixels. That's going to be an 8 by 8 tensor. Take the weight, 8 by 8 tensor. The threshold term and the output should be something. So let's take the input. The input is the input, so it's going to be a variable. So I'm going to say I want an input variable which is of shape 8 by 8. That's my tensor. Fine. I'm going to create weights, so that's not an input, that's a parameter. This is also going to be an 8 by 8 tensor, so it's actually not quite what I did here, but like ignore this, like this is a technical detail. I'm going to put a number, which is my threshold, which is now one number, which was like the threshold for my gate. And I'm going to build my model. And so my model is going to be simply this. Take the weights, that's a tensor. Take the input, that's a tensor. Compute the multiplication, so that's CNTK times. I'm multiplying these two things together. That's going to give me like a function. Take this, add this to the constant, and then pass it to my gate function, which is here going to be called a sigmoid function. So what I'm getting here, I'm composing here something which takes inputs and weights, creates a function which I should be able to run. So this is what CNTK gives you as a building block. CNTK lib is going to give you a bunch of operations which allow you to operate on tensors. So I have things like absolute value, arcos, add, multiply, all these things. So what you can do is you can create operations on tensors and create functions. Good. So the label is the thing I'm trying to predict. So that's going to be a number which is going to be between 0 and 1, whether it's a 1 or a 2. So let's do that. And now my model is formally defined. So what I need is I need to read data, pass examples to it, and let it iterate until it finds correct answers. So let's check that out. First thing I need to do is I need to tell it, what do I mean by the answer is close to what I want? So this is what people call the loss function. So the purpose of this is going to be whenever I run an example through the model, I'm going to get an answer, and it's going to look at is it good or bad, and it's going to try to make the loss function smaller and smaller and smaller. So that's what the algorithm does. Learning rate is not very important. Also, as a side note, what I'm showing you here is pretty ugly code. So what I did here is I took the library like out of the box and use it like without my library, without stuff like that. So the good side is like it works. The bad side is like quite painful, which is kind of the point. So now I'm going to tell it like, fine, I want you to learn using the parameters. So my trainer is going to be taking that model, taking that loss function, and is going to use SGD, the stochastic gradient descent, which is the learning algorithm I want to use to reduce my weights. Good. Now I need to read the data. So if you recall, like my data set or my file had something called labels and something called pixels. So here I'm telling it, whenever you read the data, you're going to see something called pixels. You're going to have 64 values. Whenever you get the labels, you're going to get 1 value. And now it's like what I need is I need to set up a reader. So look at the data which is in the file called images and read infinitely, like keep going and going and going over the data set. More painful stuff to set up. I'm going to tell it I want to run on the CPU. I'm going to read by batches of 64. So again, like this is not the most pleasant code, but like now we're set up. We have a model, we have a reader, we have data. So what we should be able to do is like run 1,000 passes, and on each of the passes, what the model is going to do is like it's going to take the data, read the data from the file, pass it into the function, train it, and try to reduce the weights over and over, try to modify the weights so that the loss function goes down. So let me run this. And so now is like we're doing some learning. So what you can see here maybe is that we started with a loss function which was initially pretty high. Like initially, the loss function was giving us like 0.38. So this is bad. This is meaning like in general, the error we're doing is pretty high. And over 1,000 steps, as you can see that the loss function goes down and down and down and down. And like after a couple of thousand iterations, I get something which is pretty close to 0, which is telling me at that point, it looks like the model is actually predicting the correct thing. It's typically predicting what I want. So good. So now what I want to do is the following. Is like I told you, if the model is working the way I expect it to work, this is how the weights should be looking like. So what I'm going to do is I'm going to actually look at the weights which the model gave me back. So let me do it here. So the code here is not particularly important. but I'm going to show the weights. So like this is going like, I'm going very retro, keeping with the theme of like old school games. So I have a WinForms visualization. What I did here is like I plotted on an 8x8 grid the weights my model learned on my sample. And so what you can see here is like whenever you have something which is dark, like it means like the weight is close to 0. So it learned that that pixel is not very useful in making predictions. Whenever you see something which is strongly yellow or like yellow, it means like the model thinks that is useful in recognizing a 1. And when the weight is blue, or like very light blue, it's going to tell me that this is useful in recognizing a 2. And I would argue that the shape I'm getting here is like pretty close to what I told you I should get. What I see here is I see a shape which looks a whole lot like a 1 in the middle. Also, like I said, like this pixel should not be active because it's used both for a 2 and for a 1, so that should not be used. And at the periphery here, I see the shape in blue of a 2. It's not perfect. I had very few examples, like it was noisy. But like what I'm getting here is exactly what I predicted I should be observing. Or like not exactly, but like say exactly plus or minus epsilon. So, so the point here is like I'm not proving that it works, but at least at that point, hopefully you believe that I'm not full of lies, and what I'm telling you is plausibly true. Cool. So this is how you would learn a model from scratch, doing it the hard way. Now, let me go back to the slides for a second. Yeah, the point was that I expected something which looks like this, and what I got is something which looks like this. Not quite the same, but close enough. Good, so let's go back to CNTK for a minute. And the statement I made when I ran through my script was like, the code I showed you was like a lot of, was very verbose. I wrote a lot of things, it was not very clear. And at the end of the introduction, what I said was that what you're trying to do with a deep learning model, you want at a high level to define an architecture with components, you lay them out, and then you learn. What we had was a lot of low-level code, a lot of plumbing, a lot of wiring things together. This is not pleasant. What we would want is that we want to compose layers the way I described before. Like, and so that's kind of what I tried to do with F#, like take the raw library and do a couple of utilities so that it's actually nicer. Some of the inspiration came from a library called Keras, which is like a library which is, I think, merged now in TensorFlow, which is like which essentially is a DSL to create like nicer models. So can we do better? Sure, we can. So my aim here was not to do everything. So in general, CNTK allows you to build models which are as complicated as you want them. You could have a model like the one on the left where you have like different types of input. You could plug them into different layers. You could have like forks. You could have joins. So you could build like expressions which are as complicated as you want them. This is nice, but this is a bit complex. On the other hand, is like there is a subset of models which is called sequential models, which looks like the thing on the left here, on the right here. And so a sequential model is saying, like, if you give me an input, I'm going to push it into one layer, push it into one layer, push it into one layer, and at some point, I have the output. As it turns out, like, a lot of models are sequential. Like, typically, when you do an image recognition, you take an image and you pass it to a layer, 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 to the output, all of this. So even though it's not complete, like, sequential models are quite useful and cover a lot of ground. So I figured, like, how about I try to do something for sequential models? Also, if you've seen F# before, is like this should sound familiar or look like a pattern which is quite common, which is the piping operator. Like if you look at F# code, typically what you have is something like this. I take inputs, pipe it into a function, pipe it into a function, pipe it into a function, and at some point I have an answer. So what I'm after is exactly that. What I want is to build a model where I'm going to take an input, which is going to be a tensor, and compose transformations. Each of them are layers which are going to transform to the output. So let's do that on a classic data set. So the classic data set I want to talk about is the MNIST data set, which is it's kind of the canonical example for lots of demos. Like the goal is to recognize numbers which have been written by a human on a sheet of paper. So what we want is that we have numbers, and we want to take an image and say, like, this is a 1, this is a 7, this is the 3. The architecture we're going to use is what's known as a convolutional network. So this is a stack of layers, 3 types of layers. A convolution is similar to the type of filter described before. Like a convolution is a filter which is going to scan an image and ask, like, did you find this pattern somewhere in the image? And so you have a convolution layer, and then is like it's going to feed into an activation, like did I find this pattern or not? And then you put another convolution up to the end. I mean, the details are not super important, but like this is the architecture we're going to use. So the input we have is like a bit more complicated than before. These are images which look like this, like they are like a grayscale, and they're written by humans, so they're not particularly clean. And what we want is like, if you give me a 3, I want the system to tell me this is a 3. So let's do this. So I'm going to go back to VS Code. And now I'm going to go to show you a bit like the type of thing I have been trying to build to make like the library more palatable and make it possible to compose models. So initially, I'm going to load my code here, and I'm first going to reset my session. Let's do that again. Here we go. Sorry about that. There we go. So the data we have is a bit more complicated than what we had before, because now it's like I don't have 64 images. What I have here is a data set of 5,000, so that's a bit more. And now what I have too is like instead of 8 by 8, I have images which are 28 by 28. So I'm actually learning on a lot of pixels. Like I'm learning on about like 800 pixels. So that's a lot more data. The other difference we have compared to before is like the data set is using something which is called one-hot encoding. Please let me do that. So each of the images can be one of 10 things. It can be a 0, a 1, a 2, a 3, and so on and so forth. So the label I'm trying to predict, the encoding I'm using here is, if you look at each of the lines here, I have 10 numbers. 9 of them are 0, 1 of them is a 1. So what this is saying is like this image is not a 0, is a 1. The one which is on 1 indicates the position of the image we're trying to predict. So the first one has a 1 in first position here, saying like this image is a 1. This image is a 0. This image is a 1. 0, 1, 2, 3, 4. This image is a 4, and so on and so forth. So that's the data set we're going to use, and what we want is like to learn weights which are going to recognize these images automatically. So let's do that. So now what I have is like I don't have, my output is going to be, my input is going to be a tensor which is going to be 28 by 28, like much bigger images. And my output is going to be not one number, but 10 numbers. It could be a 0, it could be a 1, it could be a 2, so that's fine. And here, like most of the work I did revolved around like making layers nicer. So I'm going to use two things. I'm going to use a convolution layer. So a convolution layer is essentially a filter of a certain size which we're going to scan on the image. The details are not particularly important, but here I'm saying like the component I want to use has size 3 by 3. Done. Pooling is something similar, which I'm not going to talk about, but it's a component which is 3 by 3 as well. And now all I need to do is I need to define how my network is supposed to work. So I want a sequence from input to output. So this is going to be a computation or a function, and I'm going to simply stack operations together. First thing, I'm going to scale my input. Then I'm going to add one layer, wet layer, a convolution, and what I want is like I want 4 types, 4 filters of the type I defined before. So I want you to use 4 convolutions. Next layer is I'm going to activate. Then I'm going to put another convolution. And here I'm going to say, how about you use now 8 filters? And I'm going to stack more things. And I'm going to put and so on and so forth up to the output. So the thing which is nice here is like instead of this very low-level function description, now I'm directly saying is like I want you to take like this type of component, put 7 on them, stack it, stack it, stack it. If I want to change my model, the only thing I need to do is I can change it to 16. I can start to insert, remove layers, and see how different one works. So I'm in a much, much better place. First, my model is much more readable, and then it's much easier to change the structure or the architecture of my model and compare different models. So my network is done. Specification, here I'm saying like great. Now features are going to be the thing I told you, labels, the thing I told you. The network I want to use is the thing I just described. Loss function, we still need that. And now all we need is to set up the readers. So let's do that. I still need to read labels and features. I'm going to define like, please take the data set of like 5,000 and read it by blocks of 60. I want this to run on a CPU device. I want you to find a text file which is going to be called training. That's the one I just showed you. And now I should be able to just learn it. So let's start the learning. And so obviously, so now instead of like 64 images, we have 5,000. Instead of like 64 features, we have like 800. So it's going to take a bit more work. So now you can see like the machine in action. And what it is doing, you can probably see that the loss function is getting lower and lower and lower. Again, we started with a pretty bad loss, meaning like the model doesn't know what it's doing. But as we go, is like the loss function is getting lower and lower and lower. And what this is indicating is like the model is actually learning how to predict zeros and ones and twos and threes. So we should arrive soon to the result. Unfortunately, I don't have a GPU on my machine. If I had, like this would run blazingly faster, but I have a Surface, so doesn't work. But like now I have a model. What can I do with it? Well, it's like the first thing I can do is I can save it. So this is neat. I mean, it's neat. It's not fantastic, but it's useful. If I look at the way the model looks, it's like this is this file here, which is not particularly readable, but like in one file, it saved like the structure of the model, saved the weights, saved everything. The thing which is nice is like I could take that exact model, I could load it from Python, I could load it from C#, I could load it anywhere. Like this is the model. This is all you need to make predictions at that point. Cool. So let's do that. So I'm going to now take that model, and I'm going to test it on a different data set just to see what results it gives me. So that's fine. So first, like if I do that I have a data set of 500 images which I use for testing, and it's telling me that on 500 images, it's making 9 mistakes. So that would be like, what, 4.5%? It's not perfect, but it's pretty decent. You might not trust the numbers, so let's look actually a bit at how this looks. So here I'm going to take a bunch of images, and I'm going to see what the model does. So this was a 3. And again, not to make repeating the point, like these images are numbers which have been written by humans, so they're actually pretty dirty. And like the model is telling me like it's a 3, and I'm predicting it's a 3. So it looks like it did pretty well here. Here I have a 1, recognize the 1. A 1, again, recognize the 1. So these ones are not too difficult. This one is starting to be a bit harder. Like again, like this is a 5. The model recognized the 5. Like not too bad. This one is okay. I don't know what I would have guessed for this. Like, I don't know, but apparently it was a 7, and the model was right. 5 again. Like, even like with the smudge here, like the model recognizes it's a 1. Like, so long story short is like it looks like it's not a proof, but like it looks like after my couple of iterations on my tiny machine here, is like our deep learning model is actually doing a pretty good job at recognizing all sorts of numbers written in all sorts of formats. Yeah, let's do that. Yeah, look at this. Like, apparently this was a 2, and like the model is right again. It's funny, I think the model will be better than me at actually recognizing what people write. Okay, so I'm going to close this and go back to my slides for a second. Yep, cool. So conclusion is like first is like what I showed you here was sort of specific to CNTK. I showed you 2 things. One was general ideas about deep learning networks. What I described in the beginning is true of pretty much any library. Like it's not specific to CNTK. This is kind of how a deep learning model works. And the things I showed also, like which were CNTK specific, if you look at the documentation for TensorFlow, it will be pretty much the same thing. Like every deep learning library kind of looks the same way. So one thing to know about CNTK is like it looks like they stopped the development, so there is just no new addition to the library at that point. So like if I were to start now on deep learning, I might look at TensorFlow rather than CNTK, but like again, like the ideas are similar. The code I showed, you can find it under CNTK F# on GitHub. I also wanted to thank a guy called Avi Avni who helped me out with it. And there is another person who has a CNTK library with F# called FSCNTK. Beyond that, so I talked about CNTK, and you might ask, so how about TensorFlow, how about PyTorch, how about other libraries? Can I do something with it in .NET? When I started working on CNTK, CNTK was the only thing I could use. Since then, people have been also working on making it available for .NET. So on TensorFlow, you have like TensorFlow.shop, which is bindings from TensorFlow to .NET, and another specific project I want to mention, which is TensorFlow.fshop, which is a project by Don Syme and Matt Moloney, which is actually super interesting. So I want to show you that because it's kind of cool. So what the thing does is like on one side is like you have bindings which allow you to call TensorFlow from .NET. But one thing which is pretty awesome in what they've been doing is like Don and Matt have been working on a mechanism to help you make sure that the computation you write is correct. Like if I take a step back, is like what I described as like every deep learning model uses tensors. So tensors is like multiplying arrays together, 2D arrays, 3D arrays, all these things, and it's very easy to do mistakes. It's easy to do mistakes because if I take 2 arrays which have different size, the type system will never tell you that you're trying to add an array of 10 and an array of 20. The code will compile just fine. So you will get like runtime exceptions. If you make that on 1D array, 2D array, 3D arrays, that type of error is quite common. It's difficult to get the model right. So what Don and Matt have been working on is something like this, which allows you to actually live check if your model is reasonable. Like here you start with adding 2 vectors which are of dimension 2, like 2 arrays. And now if I start to put a 3rd element here, the compiler is immediately going to tell you this doesn't work. you're trying to add arrays which are of incompatible sizes, which I think is absolutely beautiful because that's a huge source of error. So I think like this project is something which I keep my eye on, and I hope we'll get somewhere because it's quite useful. Or it does something quite useful. And I think that's what I had on that topic. So yes, I think that's all I had. So it's like the first thing I want to say is I want to say thank you. Again, like my name is Mathias. You can find me on Twitter. All the code I showed, all that stuff is on GitHub. Lots of stuff also related to it on my blog. And that's what I had. So thank you. And that's it. Yep. And I think we even have time for questions if people have questions. Yes? The question is, what's the difference between ML.NET and CNTK? It's a good question. So ML.NET is a project which has been pushed pretty hard by Microsoft over the last year, which is now, like, I think at version 1.4 and is pretty mature. They're kind of in a different space. Like CNTK is purely about defining deep learning models. Like your whole goal is to define a function which works with tensors and learn using that. ML.NET is closer to something like scikit-learn on the Python ecosystem. It's more, at least the way I view it, is like it's more of a place where you can go and you can find a collection of algorithms. It's not focused particularly on deep learning, but you will find things like classical regression, like trees, forests. So it's more of a collection of algorithms which you can use, and it's typically for. I would argue that ML.NET is probably going to be more useful to you typically than CNTK. Like, because to build a deep learning model, you will need typically a lot of data. It's awesome as long as you have a lot of data and it's a bit fickle. ML.NET is like a smaller, simpler algorithms which will typically work with smaller data sets and which are maybe more directly usable for business applications. So they're in different spaces. ML.NET is more like for smaller scale data sets. I know they're doing plugins so that you can also import deep learning models, but it's not the focus of the library. It's more of a catalog of things you could be using to do a machine learning problem. Other questions? Yes? The question is, could you use F# quotations to define these functions? The answer is probably yes. What I'm not sure about is like, what would I gain with the quotation? Like the one direction I have tried on this one was to use a computation expression. The goal was a bit different. Like the goal was, one thing which really annoyed me with the low-level library was that it was quite possible to write half of the code saying this is running on the CPU, other half of the function on the GPU, and then put it together. And guess what? That doesn't work because like it's either CPU or GPU. So I tried to use computation expressions for that. So why? How do you think like a quotation would help? Okay, so I have not thought about quotations to do that, like, but I have. That's one thing I have done. Like, if I look here, like well, okay, maybe that's not visible. So that's part of what my library does. Like, what I did with my library was making it easier to create a tensor and do things like, hey, I want to multiply tensors. How about I use multiply? So I've done that through a different direction in the library. More questions? Yes. Can I comment on deepfakes? Not from a technical standpoint. I don't have much to say about it. Like these are fun projects. As a human or like as a citizen, it looks to me like one of the examples where I think machine learning for me is scary, not in the way people expect it. Like a lot of people get excited or scared thinking about Skynet and machine learning taking over the world, getting sentient. Like the thing I'm much more worried about is like what humans do with machine learning. And so in that sense, it's quite worrisome. Like deepfakes is this thing where you take a lot of samples, and then it's like you actually use a deep learning model to create things which look like humans or create things which look like human text, like create things which for all intents and purposes look like they have been created by a human. So yeah, I think it's tricky because you see already like with the real news how people have a hard time discerning like what's true and false, and deepfakes are making that quite scary. But that's I'm more concerned as a citizen. As a technician, is like I don't have much to say on the topic. Yeah, humans are more scary than machines. Yeah. Good. So how about unless there are more questions, how about we stop there? So I wish you like a great rest of the conference. And if you want to see more of me, tomorrow I will be talking about something completely different, which is Dungeons and Dragons and F#. So if you're into Dungeons and Dragons, come and see my talk tomorrow. Thank you.